Okay. See the screen?
Yes.
Okay. So, okay, everyone is there. Okay. Hello, everyone. Welcome to this guest seminar series organized by the UNESCO Chair in Disaster Risk Reduction and Resilience Engineering at University College London. This chair is chaired by Professor Dina Dayala at UCL, and I will be introducing the chair's activities very briefly, and I will also introduce the presenter for today. So let's move on to. So in the past, we have done almost seven of such kind of seminars already, and you can find the recordings, video recordings of the seminar online at our YouTube channel, Epicenter YouTube channel. If you go to our website, you can find the recordings as well as details of each of these talks. And today we are here with the SMARTnet non-engineered seismic design version 2 that will be delivered now by Mr. Martijn Schildkamp. And in the next months, coming months also, we have a series of courses, as you can see in the screen. Besides these educational seminar and talks, we also have ongoing research activities within the UNESCO Chair. We have mainly 3 projects currently, assessing the resilience of the schools and road infrastructure in Philippines, using artificial intelligence to determine the resilience of the school infrastructure in Dominican Republic, and the structural and functional resilience of the schools in developing countries like Nepal. So the detailed introduction and scope or methodologies of these different projects, you can find it online at our website. This is the website, UCL, Epicenter, and the UNESCO Chair. If you go to this website and then see here, you can find the partners and collaborators, research activities, educational activities, under which you can find the seminar and talks. And we also have a series of publications relevant for the disaster resilience of the schools, if you click this link here. So today, the talk is about, the title is SMARTnet, a non-engineered seismic design version 2, which will be delivered by Martijn Schildkamp. He's the coordinator of the SMARTnet project. Let me introduce briefly Martijn. So he's, one second. He's an architect and has over 10 years of on-site design and building experience in various pre- and post-disaster scenario projects in Nepal, Sri Lanka, India, Indonesia, and so on. He holds a PhD in engineering on the title Seismic Behavior of Nominally Reinforced Rubble Stone Masonry Buildings. And currently he coordinates a project with 25 masonry experts from all over the world, trying to assess typical rubble stone masonry buildings from the Himalayan belt. So I will now pass on to Mr. Martijn Schildkamp, and he will do the talk now. It is a 2 hours seminar, and let's hear Martijn now. Thank you.
Yeah, thank you, Rohit, for the introduction. Now I need to find my, you have to enable my sharing, I guess.
You can share now, I think.
Oh, yeah. There we go. All right. So, good afternoon, everyone. Well, thanks for the invitation. Am I coming through loud and clear?
Yes, we can hear you, Martijn.
Good. All right, here we go. All right. Okay, what I want to show you today is two things. Let's see if this, yeah. So my name is Martijn. I started basically as an architect about 15 years ago, working in developing countries. I started Smart Shelter Foundation, which is a small NGO. But out of that came a consultancy, which is me giving workshops at universities worldwide. And based on that, we started developing research assignments for students all over the globe who are basically helping us now. And also with our last project, SMARTnet. I'm going to explain all this today, and I do it in two parts. The first part is where I will show how we built our schools in Nepal, let's say between 10 and 15 years ago. But we did this before the earthquakes in 2015. So it will be interesting to see how we managed to do this. And then in the second part after the break, I will show you the state of the art in research and how we are trying to tackle some issues at the moment. So I started as an architect myself. My first time I went to work on projects in developing countries was in Sri Lanka after the tsunami. I was in charge of a rebuilding of 170 houses on the east coast of Sri Lanka. And then the year after that, I went to India, where we started building a school with earth blocks. So basically, the moment we started digging foundation, the earth that you see in the back, we started using to make blocks. So we provided jobs in the village. We made about 6,000 of these stabilized earth blocks. They're dried in the sun, and we built this school. But I want to talk today about something else, which is the earthquake-resistant schools we built in Nepal, and especially the ones we built in the mountains. So what we had to do here is we had to focus on something called non-engineered earthquake design. And at that point, I was an architect. I had to learn this myself. But what we very quickly understood is, okay, people generally have an overly low overall knowledge. What we often see is what you call inferior construction practice. There's at that point, there was a lot of shortage of material. There was hardly any infrastructure. There was power cuts every day for 8 hours. So what we had to do is we said, okay, we're not going to introduce difficult things or what we call aliens, but we're going to stick to something what the people know. So let's stick to the local building knowledge. And then, so the first thing we had to do is we had to do an assessment. So we literally walked to the village that had a request for help. And usually we could see very quickly, okay, yeah, help is needed here for sure. So this is a school that is cracked from top to bottom. Here we see cracks in the corner. So we see that there's dislodging in critical details of the school. Remember still that this is before the earthquake in 2015. But schools already collapsed, let's say based on due to 20 years of light trembling. But the biggest issue was low construction quality. So this is what we saw, and then schools either asked us for help, and well, we decided to do it or not. What we then did is that we started grouping the schools, so to make it a bit easier for us. So we put, let's say, schools in line so that we could easily visit them. But this is maybe the most important person in this whole project, which is, his name is Damodar Bhaktatapa. So he was a project manager in Nepal. At this point, he was a bookkeeper, but over the years, he learned about seismic design or non-engineered seismic design. And I consider him one of the better engineers at this point. He just learned by doing. But without him, we could not do this project. So he did all the communication, all the administration. And while we were visiting these villages, he was the person that made things happen. And this is things, of course, that I cannot do simply because I don't know the language. But also Damodar had this sort of a natural born leadership. So he was really the key in the whole project. And why was it so important that we start doing this assessment? Well, this is an example of a school that had 7 classrooms. And they basically asked us to replace all 7 classrooms. But then what Damara could do, he could go back into a little bit into time and see, okay, what happened there with these schools. And then he saw that, especially in the last few years at that point, and they had, what you see here is Nepalese calendar. But in the last years, you saw a decline in students in the classrooms because this school was fairly close to the city and there was a lot of migration happening. So what we could see is that we're not going to build 7 new classrooms for just 100 children. I mean, that was, at that point, there was only 80, I believe. So what we also saw is that other organizations already had put their quite large classrooms. So we said, well, why don't we put one wall in the middle and split this one in 2 classrooms? So this is our first step of cost saving. So this is things that that Damara can do. I can't do this. He knows about the situation. He knows that something has changed and that there's less and less children going to school. So it doesn't make sense to build 7 classrooms. Okay, step number 2 is the design. So this is where I start coming in. So I had to learn the basics of non-engineered seismic design. And we built schools in 2 types. One is with rubble stone. So this is what I mean, stick to what we know locally. And I made the design, and we even managed to do this in the Nepalese language. The other technique that we did was hollow cement blocks. So the closer we came to the city, the more cement blocks we saw becoming available. Basically, transportation was easier. So it's either rubble stone or it is the thinner walls with the blocks. But this is what we did not do. We were very specific about one thing. We said, okay, we're not going to build those aliens in the mountains. We're not going to build concrete frames. The reason is people basically can't make it. I'm going to, at the end of this first presentation, I'm going to show you some examples, also a little bit related to the horrible events this week in Turkey. Then a second thing we did is we made an estimate. And this is a local estimate, which is just 1 page. And we learned that the local engineers could only make estimates based on concrete frames. But we, of course, we were building rubble stone masonry or cement blocks with certain reinforcements. So this didn't make any sense. This was the only thing they basically could make. So I had to make this myself at one point. And I made 15 pages, super detailed estimates. And then the third thing we had to do is we started doing training. We were lucky sometimes to have a little bit of electricity, so we could give some training to the local masons and carpenters, but also to the villagers, to the headmasters of the school about what we're going to do. But we found out very quickly that, okay, talking about seismic plates and fault lines and things, people had no idea what we were talking about. So this became quickly, it became too difficult, especially when you keep in mind that that original mythological belief in Nepal is that the earth is flat and the earth stands on 4 elephants, and the elephants are standing on a big turtle that floats through space. And if the turtle gets angry, the turtle moves, and if the turtle moves, we have an earthquake. So yeah, here we come with all our difficult talks. So okay, we learned quickly that that was not the way. For you, of course, I can do it. So what I'm going to do now is I'm going to give you just a brief overview of what we call the rule of thumb of this non-engineered seismic design. So, and it is not very complicated. So rule number 1 is, okay, don't build on slopes. Stay away from edges for about 3 meters. I don't know if you hear all these bells and things, because this is when people come in the waiting room. Is it possible to switch that off somehow, maybe? Or people leaving now. So, okay, rule number 1, do not build on slopes, because that's dangerous. The closer you are to an edge, first of all, it means a very uneven settling in your foundation. That's one thing. And the second thing is, yeah, the closer you go to an edge, you have the risk of landslides. So sort of the rule of thumb is stay at least 3 meters away from these edges, but preferably further. Rule number 2. By the way, you don't have to write this down. I will send a handout later about this. But I also will explain later why you don't really have to write this down, because I'm not 100% in agreement with most of these rules. Rule number 2. keep it simple. So simple symmetric shapes. This is a quite important rule, by the way. So squares, rectangles, round buildings would be preferred, actually, because you don't have corners. And this is what we see in many places in Nepal, but also in many parts of Himalayan region. So shape-wise, this would be perfect. But the thing is, these little houses, they miss all kinds of reinforcements. So they're still pretty dangerous, but shape-wise, they would be perfect. So don't build all these difficult shapes. Don't build very long buildings or U shapes or T shapes, because these will have the tendency of to move during a seismic event. Or don't, for example, all of a sudden go from 1 story all of a sudden into 2 story, because you will get trouble here where these 2 buildings connect. And you can basically already see it here, right? This building starts to tilt a little bit to the outside. So this is what you must try to avoid. So keep it simple, because in these difficult shapes, you will get otherwise the tendency to start that the building starts rotating, and rotating means shear cracking in the T sections and the corners. Like here, this is a picture from Indonesia. So there you then see the very typical diagonal shear cracks in the building, or this one. So keep it simple. And what you then should do, instead of those difficult volumes, what you should try to do is cut it up in smaller volumes. So then each of those little blocks, they're quite simple to make earthquake resistant. So for example, what you do is you either make a small gap between these volumes. What we learned here is that on paper, they say 3 centimeters is enough. But what we learned in that it is not practical for masons to work here. It's very difficult to get your fingers between this little gap. So we went slightly wider at least 10 centimeters later on, but keep the volumes separated. Or here as well, here you see 2 volumes where there is a corridor in between. So small little volumes within a certain dimension. So what we did is we have a width versus length of maximum 1:3. So that means that what we did for our schools, maximum 6 meters wide, maximum 18 meters long, or 3 classrooms maximum. That's the maximum we did in Nepal. For people that came in slightly later, what I'm showing now is what we did before the earthquake, so before 2015. So maximum free span, we did 6 meters, 1:3. You could potentially go with buttresses, so make it one big room. But again, I would advise against it. I would at least make interior walls for better stability. So 6 by 6 maximum dimensions is what we did. But also in height, there's something about here. Here you see a very high wall with basically no connection to the floor in the middle. So this is way too high. And then this whole pane of masonry started to disintegrate and fell outwards. So also in height, what we do is we say for bricks and blocks, maximum 3 meters per story, and for stones, maximum 2.8. But I personally don't go with a double-story stone building myself. I find the risk too large. And here you see an example of a picture I took after the Pariaman earthquake in Indonesia, in Sumatra. This is, first of all, it's just 1 brick thick walls, so it's not thick enough to begin with. But you see here, everything above this line is basically already too high. So you can imagine that these walls can't resist all this earthquake force in any way. And that's basically what happened here as well. So maximum height is also important. Then probably the most important rule here is the horizontal reinforcements. And at this point, we advised to do this at all construction types. Basically, we say wrap up your building like a small present. But what it means is that you create box behavior. And without box behavior, you have the risk that your walls either crack or completely disintegrate and dislodge, and you create out of plane failing. So we did in our buildings, because we were in a high seismic zone, we did reinforcements at 5 levels. So the first one is on top of the foundation. The second one is the sill beam, which is below openings. There is a lintel, which is on top of all the openings. There's a top beam, And there are stitches in the middle just to break the height here and create some extra break, so to speak, to avoid shear cracking in the corners. We said do it at all types, but there's in, let's say, low to medium earthquake zones, sort of the consensus is that 2 should be enough, maybe the one on the plinth and the one at lintel height at least. But like I said, we did it at 5 levels. And then we also showed what we do. So we painted this on the outside. And in our first designs, we had an extra one, which is this one, is the gable beam. But I will show you slightly further on that is quite difficult to make. So we doubt that this is really a good addition. Then there's a rule number 7, which is about vertical reinforcements. And here, now the controversy will start, which I will do, I will explain in the second presentation in far more detail. But what we said is that, yes, at the thinner walls, we definitely put in vertical steel reinforcements. So you create now some sort of a cage-like effect together with the horizontal bands. So we say, okay, at the thinner walls, brick and block masonry, let's say up to 20 centimeters thickness. We do 3 bars in the corners, and then we say we do 4 bars at the T-sections. And we do something next to all the doors and windows. And the interesting thing about these hollow cement blocks is that it's very easy to put something vertical in there. I mean, the holes are basically already there. So you start building your wall. So you slide the blocks over the steel bars, and then you fill that up with a lean concrete. So here you see it in the T section. So there's 4 bars, and the bar that you see here is the one that will come next to an opening. So at the top of the wall, you will see those bars sticking out. So that means that this is a thinner wall, which is also reinforced with vertical steel bars. And this is an example of Sat Premaini, one of his projects in the Terai in Nepal. He built with stabilized earth blocks, but in an earthquake-resistant way. So he also included vertical steel bars. All right. So vertical steel at the thin walled structures. Yes, we know that it works. We know that it absorbs earthquake forces. We know that it prevents shear cracking. We know that this works. But what to do now with these very thick walls? I'm going, like I said, I'm going to explain this in much more detail in the second presentation. But we feel that it should not be there. And well, okay, let me not give it away straight away, but we didn't do it. Let's put it like that. What we did is we made sure that we had a lot of bonding in the walls. So what we call through stones. And we also invested in cement mortar. So yes, of course, that's more expensive than mud mortar. We know that. But these two, this combination of elements for us was enough. So in our schools, there's no vertical steel sticking out. Like I said, I'm coming back to this in the second presentation. All right. So we said, okay, we invest in good bonding, through stones, and cement mortar. Then there is something to say about maximum dimensions of openings. And well, different codes, different rules, different manuals. But roughly what we said, okay, in corners, we at least we make sure that there's a wall panel of 60 centimeters, but preferably 90 centimeters. And also what you should not do is you should not exceed 50% of openings, of total openings of the total wall surface. So this is examples of where it went completely wrong. This little bit of masonry here was supposed to deal with the total earthquake forces, and it literally exploded. It just couldn't handle all that force. So here we see too much opening versus too little masonry panel that should resist the earthquake force. And here, this is an example of a school in Nepal, where you see that there's an interior wall here. So that means that this door is placed way too close to this surface. So that means that that interior wall is basically sort of standing loose. There's no masonry around it that keeps it together. There's also uneven settling here because of this this difference in height and ground. And what is very important is that the doors must always open to the outside. And this was an issue. This was a cultural issue. I mean, in Nepal, it is standard is that the door opens to the inside because you want to welcome people inside. But we said, no, absolutely not. They must open to the outside. And then we showed always this example of a school that an interior wall that collapsed, and all these stones were blocking this door. So luckily this happened when no one was inside. But you can imagine that if there's an earthquake and the door gets blocked for whatever reason, then people can't escape in any way. So doors must always open to the outside. All right. Rule number 9. This is something that we did not have to deal with so much because we only went 1 story high. But there's also rules about vertical regularity or irregularity. This is examples of Tamil in Kathmandu. I would have expected that many of these buildings would have collapsed during the earthquake, but interestingly enough, most of these survived, even though they're already tilting before an earthquake came here. But you can imagine that this is something that you would like to avoid. And also, what you must always make sure that there's a load path down that is straight. So something is missing here and there as well. And it can be the result. This is a picture from Indonesia in Padang area again. But I also saw many of this horrible pictures in the Turkish earthquake last week, where there seems to be a lot of buildings there with soft story, with parking on ground floor or shops. And this is a picture from India. But those ground floors then, if they have no structural resistance, they literally get slammed out, and buildings will fall on top of this. In Nepal, what we saw a lot is that there's a heavy block of masonry standing on, let's say, a layer of wood pillars, and you can already see. And this picture was taken before the earthquake, but this building is tilting in this direction, and you see this shear crack already developing here. I doubt that this has survived the earthquake in 2015. The last rule is no loose elements. Now, this makes a lot of sense. This is a roof landscape, again, of Tamil in Kathmandu. What you see here is that all these flower pots are standing here, and all these water tanks. And what I understood is that it has been raining flower pots during the earthquake in 2015. And even though many of these buildings survived the earthquake quite fairly easily, actually, a lot of people got hurt or probably even killed due to these things that fall off. So in a seismic zone, I mean, don't do these things. This is a water tank that came off, that fell off a roof. And you can imagine what's going to happen here. This is, I took this picture in Lombok in Indonesia before the earthquakes there. I don't know what happened here, but you can imagine that, yes, this is a heavy block of water. And if this is your house, you really don't want to live there. Okay, so 10 rule of thumb. We went through this quite quickly, but this is sort of the 10 rules of thumb that I also applied at my designs that we built in Nepal between 2007 and 2012, 2013. Normally I say is the question so far, but let's do that at the end of this first one. All right. Now, what we started doing now is that, okay, we already saw that these basic rules of thumb are even quite difficult to explain to masons who are used to building in a certain way for, let's say, a few hundred years. I mean, masons learn this from father to father, and they learned from their father, and they learned from their grandfather. So it means that often they know what to do, but as soon as we start to introduce, like, let's say, technical terminology, then it becomes a bit too difficult for them. So what we saw is that what we had to do, we had to start doing field training, on-site training, literally clearly showing what we're doing. And then it all made sense. So this is a little bit of technological background, but here it became more clear to them. For example, how to make your building straight. We do this with a very simple trick. It's the Pythagoras triangle. So this is 3. This is 4, then this is 5. And this is how you know that your building is straight. Very simple tricks, but very easy to understand by everyone. And then we started showing, okay, how to, what to do with these connections. But also far more important was, okay, which materials are correct. So for example, this is very fine sand, which is very good for plastering, but for concrete and mortars, we prefer more rough sand. Some rivers have that very fine sand, others have this nice, beautiful rough sand. So that means sometimes that, yeah, if you want to do it correctly, you need to invest a little bit in transportation and get the right materials from a slightly further afar, which in practice seldom happens. But at least we started teaching this. We also started showing about the right size of aggregates. I mean, people just take from the river whatever they can find. Sometimes it goes up to 10 centimeters of stones, and you just can't mix that. You can't properly mix that into mortars and concretes. And then this is the result. Steel is exposed, water penetrates in very simply, and so on. So what we did is, as a trick, we introduced spacers. And you can either do this with a pole of bamboo or with a PVC pipe. But what we did is, what you do, you fill it up with some cement and with a little bit of steel wire inside, and this is your spacer. And these spacers are being placed under the reinforcement, but also next to the reinforcement, so that your formwork, there's always enough distance, let's say 3 centimeters between your steel and the outside of your beam. And we learned about, we teach them about proper bending of steel and how to apply all these stirrups and how to bend them in the right position. And then we started introducing a measuring box. So this measuring box has the same volume as a bag of cement. So if we want to mix 1:4 mortar, then it means you empty 1 bag of cement and you add 4 boxes of these of the sand, and your mix should always be perfect. So little simple tricks, easy to understand. And the last thing we had to teach was about, well, you should not put in too much water, otherwise your mix gets too weak. So we had to do very simple, what we call slump tests, to make sure that the right amount of water is being used. So on-site training, we spent a lot of time into this, but yeah, okay. I basically lived on the mountain for 2 years during that period, and it was repeat, repeat, repeat. Now, this is a very interesting step in the whole process, which is called people's participation. At this stage, what we did, so again, we're talking about the period before the earthquake. What we did here is that we made the whole village responsible. And that means that in this case, we had to, I think it was 5 classrooms that we had to build here. So we had a piece of land. There were 60 families in this village. So a group of 12 families leveled a piece of land, meaning that the whole village worked and helped with leveling this land. But this is people's participation also became part of the budget. So this is their contribution. And we also put some money on this. This was their contribution to helping building this school, but it gives the whole village ownership. So it's not our project, it is their project. And therefore, we also managed to stay within the budget. So leveling the land is one thing, but also at some point, our materials were being delivered at the top of the mountain. What we did here, so this is the hollow cement blocks. This is not so far away from, this is about 3 hours by tractor from the city. But what we did here is that we said to the manufacturers, the little factories, we said, okay, what we want you to do is I give you 5 rupee more per block, but I want you to put in the right amount of cement. Because if we don't do this, then there's about 10 of these little factories and everybody makes weak blocks. So they're saving cost on not putting the right amount of cement in these blocks. Because if they do, that means that their blocks are too expensive and no one will buy them. So it's sort of generally known that everybody buys low strength, low quality blocks. So we said, okay, we invest in this. I give 5 rupees more per block. And then after 3 hours in this tractor, we could see that there was not so much breakage. So it means that we had good quality blocks. And then as people's participation, the blocks had to be transported down to the village. So this is, again, the contribution of the village. Okay, now we're going to start with the foundation. So this is that the triangle Pythagoras we did here, 6, 8, 10 is of course the same as 3, 4, 5, but at least the building is straight. Then we started digging into, well, the ground, which was very rocky soil, so we didn't have to go very deep. And then what we did first thing is that the foundation, here we wanted to build a school with cement blocks, so this has vertical steel bars. In the first school, we went all the way down to the foundation. And then we found out that it was very difficult to connect. So we learned here already that, first of all, we doubt that it is necessary. We probably can start on top of the tie beam, that's what we did in the next school. But we saw that we started interrupting the foundation. Now, it is sort of below ground, so I think we can get away with this sort of hybrid solution. But we learned here that it's difficult to place stones around steel bars. We did a lot of recycling, so that's good. Again, to keep the cost down, but also this is people's participation or contribution of the village, is that we started breaking down the old school building and started recycling these stones. They had to be brushed a little bit, had to be cleaned a little bit, but most of these stones went back into the foundation or into the floor filling, because why bother going into a very tough job of getting new stones out of the mountains. So this is recycling, and it also represents a certain amount of the budget of the people's participation. On average, a village contributed about 30% to the school, but it was mostly materials and labor. And then at some point we get to where we are going to put the tie beam on top of the foundation. This guy is plastering with his slipper, why not? Okay, next thing is steel. Now, the steel is an important phase in the whole project, because this is what we call the weakest link principle. The beams must be perfect because they are very important in resisting the earthquake forces during a seismic event. But when I say weakest link is this. I mean, the more of these mistakes are being made, the weaker the beam is going to be. And if those beams crack, it might result in collapse or damage of your whole building. So what we had to do is a lot of supervision here. And so we just said, okay, with a bit of chalk, we just said, okay, not good, not good, not good. And the interesting thing here is that it went wrong usually one time. And then they started realizing that I basically broke down things. And then they started phoning to the next village. They said, hey, this guy was here and he's really strict in this and pay attention. Because, yeah, like I said, it's the weakest link. We really need to supervise this almost on a daily basis to make sure that things are done correctly. And I doubt, personally, I doubt that this happened after the earthquake in 2015. But we'll get to that. So we invested a lot of time in supervision. Like I said, I lived on this mountain for about two years, and we did a lot of training, repeat. But also we made sure that the spaces were there. If the spaces were not there, I just stopped the work and I said, we're not going to cast this beam before spaces are there, because I just want the best quality. If we're going to invest in all these materials and time and money, we better do it correctly. All right. Then I always made sure that the measuring boxes were there, so that we are always mixing 1:2:4 means for concrete, one bag of cement, 2 boxes of good quality sand, 4 boxes of good quality stones, and the mix should always be correct. Then next step, for example, with the cement blocks, is that we start marking. Okay, this is where the corner blocks have to be placed, and then it must be level, it must be straight, with very simple water level and other tools. Just make sure that everything is straight and plumb. And then we mark the doors. And then at some point, we are ready for the first beam here, which is the sill beam. And also this is being marked and this is being bent. So this is rejected. This is not correct. So these little stirrups are already bent outwards. And during a seismic event, they will very easily open and crack your beam. So they really have to be bent up to 180 degrees inwards. Like I said, it is a constant supervision and repeat to get the quality that we really wanted. Now, this is the one in rubblestone. So very important is these true stones. We also did this with cement mortar. And again, we kept repeating it. So here you see how they're perfectly bent in 180 degrees inwards. And then also spaces we need to see so that the formwork is placed in the right position. So this is then something that we see, I don't know, after a few weeks at one of the schools. Then all of a sudden they go back to this quality. And then we learned that the group of masons went to the city for another project, and then new masons came here, and then so we had to teach them again how it was supposed to be done. But this one we broke down. I mean, this is going to have zero, and this is what an important one. This is on at lintel level, so this needs to be removed, and we do it again. Then another piece of community participation. So this is the wood. And the wood, this is salwood, which is a very good quality hardwood. And what I really liked about this is that the village took about a week to decide which trees they were going to cut down. And then this wood, it has to dry, it has to be seasoned for a while. So they basically say, okay, we're going to buy this, or we have this already. And then now we're going to cut down 2 more trees for the next project, but very careful with their resources, which was very good. But what I found out is that the old frames, usually the quality itself was very good as well. So what we started doing is that we also started recycling. So sometimes from 2 or 3 old frames, we made one new one. So this is a recycled frame. And again, this cuts, of course, the cost in the village. Doors must open to the outside. We already went through this. And then here you see that, okay, the walls are now finished. And now we are going to a point where we're going to attach the roof. Now, what I did say before is that we don't put vertical steel bars in these buildings, but you do see something here. Something is sticking up. So what we had to do here is we had to include galvanized steel wire into the top beam, because this is how we were going to connect the roof, because 10 years ago we could not find this in the market in Pokhara or anywhere. We could not find anchors or these J hooks at all. It was just not available in the market. So what we had to do is the first ones we still built gables, which is also something that we changed later on. But what you see here is this galvanized steel wire sticking out of the top beam. We also then tried to cast this gable beams, which are very difficult to cast anyway. And you get very weak connections here where these beams come together. But the thing I really don't like about it is that the gables could still potentially start to wobble in an earthquake and could fall inwards. So I don't like these gables at all. And we changed that later on. But in this older, the first schools that we built, this is then what we did. So we started applying the wood. We tied this with this galvanized steel. And then with many nails, we put on the galvanized steel sheets. But this is what we did later on. And this is an example from a picture in Indonesia. This is, by the way, not my project, but just to indicate how it should work. Is that what we do is that the whole roof now is made of wood, so it's light. But then what we do within the trusses is that we make some sort of a cross bracing that you can see here. So this is the trusses and this is the bracing in between. This makes the roof, first of all, the roof is light. And second of all, it makes it as stiff as we can. So under it, we also started nailing a ceiling, just to make this roof as stiff as we could. But this is one of the projects that we did, that I was involved in, that also had the same principle. Later on, what we did here is we put in some ventilating openings, and then it also turned out that the school became a few degrees cooler than normally was done. So light roof has the advantage of making that stiff, but also it reduces the risk that the gables can fall in. And then, so again, this is an old one, but what we did here is that we show what we do. So this is one of the last steps that we did, is the finishing. We show exactly where are the reinforcements, where are the beams. These schools also have buttresses. I'm not 100% sure if we really need them. This is part of the research that I will explain later on. But we show what we do. So we literally painted on the outside of the building all the beams, all the bars, and then in Nepalese language, it is literally telling what's happening there. And this is our way of keeping the knowledge into the villages. So this is our way of technology transfer. On the side of this school, the text literally says, this school is earthquake resistant. If you want to build your house like that, call Mr. Damodar, his phone number is there. And he did receive the occasional phone call. So what I've shown you here is how we built our schools in Nepal 10, 15 years ago, and how we followed the rule of thumb. And then this is the result. So this is old school and this is the new one. And again, we built 15 of these schools, replaced or broke down old schools and made new earthquake resistant schools like this. So 15 of these, and after the break, which is coming in 5 minutes, but after the break, I will show you how they behaved and what happened after the earthquakes. All right. I want to very briefly show you one more thing that we built. I just included, well, basically this morning, based on what happened this week in Turkey. But we also built one hostel for blind children in the city of Pokhara. What we did here is that, okay, I explained already, and I will show in much more detail also after the break. I explained that we don't build this in the mountains of Nepal. One of the reasons is that people can't make it. They can't meet the standard that is needed and also the cost that is needed to make a concrete frame. But what we see in the city, also many cities like Kathmandu, Pokhara in Nepal, we see many of these concrete frames. And the thing is that a concrete frame, when there's earthquake force, lateral force, or it could even be wind, a frame would have the tendency to start bending. We call it dancing. The frame wants to dance. And if it's not properly done, then this is the result. And this is a picture from the Pariaman earthquake in Sumatra in 2010. This is, you see here what happens when it is not properly detailed and the quality of the concrete is too weak. But there's two things happening here, because what's usually happening is that the frame that wants to sort of bend and dance is usually being filled up with a very stiff plane of masonry. And those two things are going to work against each other. So this is a picture of the Adana Seyhan earthquake in 1998 in Turkey. But this illustrates perfectly what I wanted to show. So in this case, the frame resisted most, but then the masonry completely cracked. But also here you see something that is called a short column effect. So we see a lot of things happening here altogether. Now, it is of course possible to make a concrete frame earthquake resistant. We did one, but the only reason why we did this is that we started building upon an already existing system, which was an animal center close to the city. But what we had to do here is that we had to add a lot of steel. And the thing is that, let's say, compared to an earthquake resistant frame and a non-seismic resistant frame, there's about 2.5 times more steel involved. So you see it's here, it's quite complicated. Well, not for us, but there's a lot of detailing happening here. And this is standard practice. So normally they just put in 4 bars, that's it. It is not tied properly. This is just some pictures, a very standard practice that I've seen everywhere in Asia. Instead of steel bars, they use sort of steel wire almost. And so the result is this. From a distance, it still looks quite okay. But the moment that we start zooming in on this connection here, yeah, then this is the result. It's not mixed properly, it's not detailed properly. And you can imagine that in an earthquake, yeah, this is going to crack completely and collapse. So for example, you see here little hooks that should have been at least 60 to 90 centimeters going inwards. So this beam has just been lifted up. This is, I think, also in Indonesia, where I took the picture. The result is this, and this is a picture from Turkey last week. If you don't build concrete frames in the right way, they're going to collapse. And well, I don't have to explain this. We've seen horrible images the whole week. So this is one of the reasons why I don't want to build these frames in the mountains. I mean, I can do it, but then I'm going to set an example that they basically cannot copy. They cannot meet. They will think, hey, this Western guy came and he knows exactly what he's doing, and the concrete is good. It is only good if you know how to make it. And that's usually the big issue. So what we do is confined masonry. And that's the point I want to make now in just a few minutes. Confined masonry, that really works. And it works the other way around. You build your walls first, and then you cast your frame around it. And those two start working together as a shear panel. And it really works. So walls first, concrete later. And just a few pictures from what we did in Nepal. So the steel is already there, but you see there's far less steel needed than what you would need in a concrete frame. The spacing in the middle of the columns is quite large. The closer you get to the connections, then the spacing gets a little bit closer, but it is still only 4 horizontal bars. That's it. So this is where you save costs. That's the first thing. So what you do, you start building your shear panels in between, and it is in a certain pattern. We call it Flemish bond, so that you get a nice tooth at the end. And then what we did, of course, we put in our spaces again. And we cast in the columns like this. And we also we show what we do. Take my word for it. We plastered this in the same way that you still see this tooth pattern. So for 20 and later it became 30 children, we built this 2-story hostel in confined masonry. It survived the earthquake with some minor cracks, not structural cracks, but it happened in one room where we didn't expect it. So we needed a little bit more research on this. But in the end, everybody was safe. Everyone could get out easily and safely. But confined masonry, I just wanted to show this in just a few minutes, that this would be my suggestion always for let's say medium to let's say 4 to 6 stories high. Go with confined masonry rather than with concrete frames, because it's proven. We know that since the 1930s, Chile and many South American countries built with this. And unfortunately, in Turkey, this was only introduced in the 2018, so the latest seismic code. And hopefully more people start building with this, rebuilding with this now. All right. This was part 1. A lot of information, I know. But what I wanted to show you is how we dealt with our construction on site in Nepal before the earthquakes. And then after the break, I'm going to be a little bit more critical on what we did. Is there any questions at this point? Or is there still anyone there?
Hi, Martin. Actually, there are some questions in the chat.
Hi.
Can I should read them out.
So I can't hear you. I'm going to just put a bit more volume here. Yeah, please go ahead.
Yeah. So the first question was, in the final picture of the school, where captions were written on the walls, there was vertical encasement shown at the side of openings. So I want to confirm, did you provide the vertical encasement to the school, vertical reinforcement or encasement to the school? I have seen around the openings.
So I really could not hear the question. Can you try one more time, please?
Yeah, is that better now?
Yeah, now I can hear you. Yeah.
So the question is whether you have the vertical encasement around the openings as a vertical reinforcement in the school building that you've shown.
Myself, no, I did not. So let me go slightly back to, so for example, it's slightly smaller now, but this one does have it because we painted this on, but that means that this is one with cement blocks. Okay. But for example, this one does not have anything vertical. Okay. But after the break, I'm going to go into much more detail. So I wanted to show you first what we done 10, 15 years ago and why we did it and how that all went. And just to give you a bit of an idea of what we had to deal with in the field. And after the break, in the next one, I'm going to show you in a little bit more detail why we did not put in the vertical steel.
Okay, thank you.
And then you may have a different opinion about it. So this is why I show this. This is, I want to start a discussion about this.
Okay, thank you.
Yeah.
There is,
Okay, there are more questions in the chat box.
Yeah.
Martin, are you able to follow those?
Oh, yeah. I see
Yeah,
chat
please.
box here. Yeah.
You can go one by one.
Yeah, let's go. All right.
So from Rohan.
Let's see.
In the final picture of his
Oh,
screen.
yeah, okay. Yes, there was same question. So yeah, again in the thin walls we did it. So that means that when you see on my schools, when you see vertical steel, it means that it is either bricks or blocks. And in the thick walls, it is not there. After the break, I'll go into a little bit more detail here.
Okay, so
Okay.
the next one is about the toothing from Noor.
The whole theory about the tooth or the teeth thing means that there's a better grip between the wall panel and the frame around it. And I have to say that there has been some research done about is that tooth needed, yes or no? And what I understood is that it is quite essential actually in the overall working of the shear panel and how this frame connects to the wall. So and it's not so difficult to do anyway. So it has definitely, it seems to have advantage, but I also know that some more research is being done on this. Does that answer the question?
Yeah.
Yeah, and maybe may I add something here? So the whole purpose of confined masonry, the confining the masonry panels, is to, let's say, increase the integrity of the panels so that it works as a single wall panel, as a complete thing. So here we are not, the purpose is not to provide flexibility in the frames, because those are unlike reinforced concrete. Those are there to confine the masonry rather than providing flexibility on themselves.
Yeah, yeah, I agree. Perfect. Yeah, it works absolutely different than a frame.
Exactly. Yeah. Thank you. And then the next question is from Sandra. So about Turkey. So you are now a ruler of Turkey. The last question, Martin.
Yeah.
So,
yes, Mr. Sander. The thing here is that this is the most difficult question, to be honest, because I don't want to talk too long about it. But the thing, what happened in Turkey is such a disaster of such a massive scale that there's hardly okay, how to start this. It is not. It should be a joint thing in my mind. It should be a joint thing in terms of, okay, there needs to be a very clear enforcement of rules. That's one thing. The thing is that I read a lot of comments about, okay, how come that there's now 20 years ago we had a big earthquake in 1999, Seismic earthquake. Then there was a lot of enforcements of codes. How come that it is not built earthquake resistant? The thing is that I'm fearing that many of the buildings that collapsed were, first of all, older than these 20 years. But we also hear now a lot of story about new buildings being collapsed. So then it is a matter of, why is it not enforced properly? Why is it not checked properly? Why is there not enough supervision? I also read something about many building companies being arrested. Usually what we see is that they started cutting costs, but in the end, it should be a joint effort anyway. I mean, they know that they are in a very heavy seismic zone. So it's not a matter of pointing fingers. It's basically a matter of joining forces and try to do it once and for all in a proper way. But I'm afraid that it's such a scale that there will always be points and phases and regions where it's just not done. I'm afraid that's the reality. This is not an easy question, to be honest. Sandertje, Sander Brouwert. All right. Shall we? I see here one more question, but this one I will answer in the next bit for sure. And my PowerPoint presentation is not going to be shared for the reason that there is some, well, in this one is not so much copyright, but I will never share my presentations because some of the pictures are that looks like something is in order, but then I mean the opposite. So the recordings, of course, will become available. I will also send a handout, but the PowerPoint as it is, I'm sorry, I can't share. And there's something then about material costs that will come in the next one. Will the recording be shared? I think it will be. All right.
Can I also add one last query? Somebody sent a direct message asking if it's okay to share your email contact in reference to training.
Absolutely.
Training buildings in Ukraine.
Absolutely.
Okay.
I will put it in the next slides in the break.
Thank you.
Okay, because I think it's time for a little bit of coffee. What do you think?
Great.
Yes, shall we have a small break?
Yeah.
All right. Please tell me what time do we start again? 10 minutes, 15 minutes?
Okay.
5 minutes.
Yeah.
All right. All right. See you in 5. Yes.
Okay, Martin, if you are there, we can start, I think.
Yeah, I'm absolutely here. All right. So everyone, now sit down and relax again, because from the introduction part 1, which is basically how I built the schools, we're now going into the more technological side of things. Someone asked about the email address. So this is 2 of them. For whatever question, please always reach out, and we'll sit down and we talk about some things. But at the end of this presentation, I'm also going to make a request to basically everyone here, and that is, let's join forces. And I'm now going to explain in what we need some help with, and how we feel that we should approach a certain thing. So here we go, part number 2. So the first part was about me 15 years ago, maybe up to 10 years ago, as an architect, building schools in Nepal and trying to figure out what needed to be done. In the second part, I'm going to show you what we're doing today in terms of research. So we looked at 15 schools in the mountains of Nepal. I showed you that we started replacing schools like these that had collapsed before the earthquake already. I explained about the rule of thumb. I explained about what we did with certain types of reinforcements. And so we built 15 of these schools in the mountains of Nepal between 2007, 2013, and then 2015, the big earthquake hit. And our schools were close. They were pretty close to the epicenter. So where you see here this green star, this is where we were. Our closest school was about 40 kilometers from the epicenter. But already here you can see on this diagram, on this figure, that most of the damage went to the other side, went towards Kathmandu. Mount Everest was lifted up even 2 centimeters. We were sort of on the better side of things. And it was pure luck, basically. It was favorable ground conditions. Let's put it like that. So at worst, this is what we had. We had very, very minor damage, basically no damage at all. We had some hairline cracks in the plaster, and then in most cases above the sill beam, and this was about it. This is one of the schools we built with rubble stone. So on the outside, you can't see anything. On the inside, it was fully plastered. We could not find one single crack. So this is one that was about 50 kilometers away from the epicenter. We checked it 3 times. We could not find one single crack. So this is that school in the back, and this is the old school building in the front, which is unreinforced masonry with mud mortar, completely cracked. The interior collapsed. The houses next to this collapsed. So yeah, okay, we did a good job. We had literally 0 damage and hardly any damage in any of our 15 projects. Now, what you see here is one of the reasons why these houses did collapse. First of all, what you see is very round boulders here. So this is coming from the river. Based on gravity, you already see the bulging of the wall. So based on gravity, those stones are already being pushed out. So imagine then what happens after an earthquake. This is done with mud mortar. Anyway, I'm going to show you in more detail in the next half hour what happened here. But the problem is this. I spotted the problem already when I was building my schools. And the problem was this, so at that point I was an architect. I wanted to figure out, okay, how do I build my schools? What must I do? And the more manuals I read, the more confused I got. And this is really a problem with many techniques at this point. The internet, everybody dumps on the internet whatever they want. And it's very difficult to find true validated information at the moment. So I already explained in the first presentation that yes, we do put something vertical in the thinner walled constructions. We know that it has benefit. We know that it works. But I also already showed you, okay, what to do with these thicker walls. And I said, we don't do it. That has a reason why we don't do it. The first reason is that when you look closely to these walls, what you see is basically it's 3 walls. Instead of one thick wall, it is a layer of stones on this side. It is a layer of stones on this side, and there's some loose stuff in the middle. So it is sort of 3 walls. And this is how people build this. First of all, they use mud mortar. And second of all, stones like this, they put in this direction. So then when we talk to the masons and we say, okay, why is it not in this direction? I mean, why don't you create some sort of a bonding in your wall? And then they say, yeah, but now I have to cut this stone, and that's a lot of effort to do. So that's basically even worse, right? They know that they had to do something, but it is basically laziness why they didn't do it. I find it even worse. So this is what we did. And I already said, well, okay, we make a lot of bonding, so through stones. We invested in cement mortar, but now the question is, should there be something vertical here? And we feel there shouldn't. For two reasons. Reason number one is that this is a very heavy building. And it means that when an earthquake hits, a lot of lateral force is being generated. Is one steel bar going to resist all that lateral force? We doubt it. Is it going to give the ductility we need? We really doubt that one bar is going to do that. But what is more important is that in this critical connection, I want to also create some sort of a bonding. So I want to create some sort of an overlapping pattern in this T section with these true stones. And that means that it's going to be very difficult to work around something vertical. We feel that something vertical is disrupting our system, that it's going to make it weaker. And that's the reason why we decided not to do it. So we deviated from the building code. The thing is that in the last 10 years, I've talked to 500 experts on this, or people that had an opinion, and it is sort of a 50-50 verdict. Half of them say, yes, it should be there because the code demands it and it will give us some ductility and so on and so on. And the other half says, yeah, you may have a point there. It might, first of all, not do much. And second of all, it disrupts your bonding pattern. Now, if we look at the Nepalese building code, and this one was revised in 2015, just before the earthquake, ironically almost. If we look at the building code of Nepal at page 34, there is a true stone. And then 5 pages later at page 39, all of a sudden we need something vertical there. This is not even possible. So what I'm saying here is that the information at the top is already contradicting and causing a conflict. It's causing what to choose here now. At the top, the information is already flawed. So that was my first point about vertical steel. The second point is about horizontal bands. So when I, as an architect, I started reaching out to some of the experts, and we came to a consensus of 5 horizontal bands, layers of horizontal reinforcements at 5 levels, which we built. And okay, we know that it survived the earthquake quite easily. After the earthquake, one of the same group of experts then said to me, well, I have a very good idea. First of all, the one under the sill, or under the windows, the sill beam is not doing so much. And it would be much more effective if we have a beam, let's say halfway the building in that shear cracking zone, which I thought, wow, okay, interesting way of thinking. And the second argument was, in Nepal, at that point, around 1 million buildings collapsed, 1 million houses and schools collapsed. Minus one horizontal band, it's going to make a massive cost saving. So I thought, okay, interesting. But the thing is that if you start looking at this in more detail, then you start realizing that, okay, if we want to create box behavior, the beam should be continuous. This is one of the strong points of these reinforcements. It is continuous. It gives us the box behavior that we need. At the moment that we look at the sill beam, so that's the one below the windows, then there's 3 doors here coming through. So this beam becomes semi-permanent, but still this will do quite what we want. This still adds to the box behavior. But now if we start shifting this beam 1 level up into that shear cracking zone, then all of a sudden all the windows come through. And then this is not really doing what we want anymore. So my critique at what is a seemingly interesting idea, my critique is that something like this, it just stays with an opinion, it stays with an idea, and it is never being fully researched and fully investigated what the implications are of this. And this is my main critique on, let's say, the non-engineered practice. It is based on opinion, and it is all meant in the best way, but it is not going to give us the confidence to continue with such techniques. So the problem is, and this is what I already saw about 10 years ago, I said, we start losing the basics. I mean, this is what I mean. Where are they now? People keep adding to this pile of misinformation or disinformation. And we seem to have lost the basics. So the solution in my mind is this. We have to start cleaning up a little bit, going back in time and figure out what it is supposed to be. And I did not make many friends when I started saying this 5 years ago. But I was given the opportunity to start researching this myself. And so this is my PhD, which is, well, the objective was very simple. What is it? What is the state of the art at the moment? And what is it worth? Now, I started doing a needs assessment. I mean, is it necessary to begin with? Answer is yes, it's very necessary. When you look at rural areas alone, and I looked at census data, then we see that in these Himalayan countries, the majority of the building stock is masonry or a form of masonry. So it is either brick masonry, stone masonry, adobe, earth, or natural materials. The blue parts is modern materials like concrete and steel. So especially in rural areas, we see that there is a vast majority of masonry, often stone masonry. And I calculated it, estimated this at over 200 million people in the Himalayan region alone. But for example, Afghanistan, where it is estimated that 80% of the complete building stock is stone masonry, large parts of China, Central Asia, there's going to be several hundred of millions more people that are still living in these techniques. Then I did a literature review. I wanted to see, okay, with all these manuals, where did it come from, and what is in there? Now, what I noticed is that there are hardly any of the manuals, and I found about 50 that are really meant for stone masonry. Hardly any one of makes a difference between the type of stone or the type of mortar. It is sort of one size fits all, and it doesn't make any sense. I mean, very round boulders with mud do not work the same like sort of coursed rubble stone with cement mortar. It's two completely different strengths and basically two different techniques. And then I also started looking at the typology of masonry. Now, what we see here is what I built. So I built, well, very neatly coursed masonry. We tried to make some rows of the stones in here with cement mortar, but also with horizontal bands. I didn't do the vertical steel. This, of course, is something completely different than completely unreinforced masonry. Unreinforced masonry, it is what it is, nothing whatsoever. This is done with mud mortar, no reinforcements in there in any way, versus the complete opposite, which is reinforced masonry. So reinforced masonry has a lot of reinforcements in there. And the last one we have already seen is confined masonry. So the point I'm going to make here is this, is that at the moment, worldwide, we have basically three typologies of masonry, which is unreinforced, reinforced, and confined. But mine is none of these three. And I want to make a very strong point for this, because it is now sort of classified as unreinforced with reinforcements. And it doesn't make sense at all, but it also starts to create confusion. And even worse, unreinforced is forbidden in all building codes. So unreinforced has already in the name itself means that it's going to be difficult to convince people that we do unreinforced with reinforcement. It doesn't make sense. So I would like to get rid of this and say we have something different. It is an absolute distinguished fourth masonry category. We can call it nominally reinforced masonry, or we can call it semi-reinforced or horizontally, whatever. What I really would like to get rid of unreinforced for this typology, because it is prohibited everywhere in seismic regions. And it's going to make a very difficult case then for us to convince people that this does work, because my schools have survived a 0.35 G earthquake in 2015 in Nepal without any damage. So it can be done. All right. So this is my first main conclusion, is that we need clear terminology and also logic, like I've just shown. And in our case, well, we need to look very closely at the masonry units, the mortar, and the typology. And I'm now have very specifically said, okay, we're going to first look at rubble-stone masonry with cement mortar, broad to courses, with horizontal reinforcements, and with flexible diaphragms. So this is not the same as river stones with mud mortars, with a concrete slab. It is something else. It needs to be very specifically described, and then we need to start figuring out what it is. All right. I also looked at where did it all come from. Now, the very first time ever that an appeal was made for building codes for, let's say, developing context was in 1977 at the 6th World Conference. Professor Arya on the right, Professor Teddy Boone on the left. Teddy Boone passed away last month, unfortunately. So at the age of, I believe 86. But to me, they are the pioneers of non-engineered seismic design. And non-engineered means, so this is specifically for the rural and the mountain areas in the developing context. The very first code ever designed was 1980, so that is super young for a building code. This was done for, let's say, stone masonry, low strength brick masonry, and so on. It was slightly revised in 1986, but for stone masonry, the chapter is completely the same. It was copied in 2004 and again copied to the letter in 2014. So the point I'm making here is that since the 1980s, which was a very good start for promoting these techniques, it has not changed at all, at least not for stone masonry. So it means in the last 40 years, nothing has been revised whatsoever. And that also means that that conflict that I've shown you in the Nepalese building code was already there in 1980. And no one ever picked up on this and said, hey, wait a minute, this doesn't make sense. Maybe we should revise this. In my literature review then, well, most of the manuals were useless anyway, because they were so incomplete that they were impossible to compare. And then with the last few that I could compare, there was no consensus on anything. I mean, the free span ranged between 4.5 and 9 meters. Everything between 1 and 4 stories was allowed in some countries. No consensus whatsoever on dimension, openings, reinforcements, details, nothing. And it shows here as well now in there's 2 codes for, let's say, non-engineered techniques. One is from India and one is from Nepal. And even here we see the differences. We see that India says, well, 2 horizontal bands is basically enough. And we want some vertical things there. And we want gables. We don't basically need anything on the foundation if it is on rock soil. Then this is Nepal. Nepal went to 4 levels, gables, vertical reinforcements, but this was revised in 2015, just before the earthquake. And this is what I do. So I do reinforcements, horizontal at 5 levels, a very light roof, and something vertical. Okay, with the risk that we're going to create a mess now, but can anyone tell me what we're doing now in 2015? What is coming here? What is happening now in 2015 after the earthquake? Can anyone guess? Just yell, and then I can take a sip of coffee. Is it model 1, 2, or 3, or something else? Okay, I have my coffee. This doesn't work, of course, with so many people. I'm going to give you the answer. After the earthquake in 2015, and bear in mind that sort of this was demanded by the Nepalese code, we now see this in many cases, and this doesn't make sense to me at all. The reason why we moved from, let's say, this to this is 2 reasons. Reason number 1 is that one German big NGO came up with beautiful drawings and sort of pushed this forward, and everybody copied. So this is that first copy-paste issue that I've already shown. Second reason is panic, pure panic. There's no other reason why all of a sudden someone tries to cram in as many bands and poles and posts and whatever in such a small building. The thing is that, first of all, you wonder why, because even the Nepalese building code doesn't require it. Second of all, we know that in these little bits of masonry, you get concentration of forces that you really don't want. So that's one thing. There's research from IIT Kanpur that shows that. But second of all, and you wonder why, that's my biggest question, why all of a sudden go to this? But then what we learned from some organizations that tried to build all this, then what you could see is that they had a lot of issues with, first of all, you have to create that gap. So you have to work around it. This is one next to the openings. And then when they start casting the concrete in between, They do it at every, I don't know, 30, 40, 50 centimeters height, and it is already pre-cracked before we have started. So it is almost impossible to properly make all these little connections. And so you get concentration of forces where you don't want it, you get very weak frame, it's not helping. And the question is it necessary at all? So, and we saw that at many examples. I mean, this is one that we already saw, that this is probably quite weak concrete or cement. But this is not helping. All these connections are difficult to make, and especially in the mountains where people don't know how to handle materials. I also wanted to include this one here. What we also saw so many times now after the earthquake is that, okay, most of the organizations there, they started focusing on training. So rather than building projects, everyone went to training masons. But then after a week of training a mason, really that's absolutely not enough. And if there's supervision lacking at all, you see, all of a sudden here we see, and I've seen it so many times, that they know that there must be some sort of a beam, but then it is interrupted at this level. So this doesn't make any sense. And it's one of the most important beams to begin with. So I'm not very happy with all these extra things that either are not necessary or are difficult to make. And even in this sort of simple building, we already see that without proper knowledge, it's still difficult to make. Okay, long story short here, my literature review showed that, okay, most of it is one size fits all, which doesn't make sense. It's comparing apples with pears. It's 40 years old, has never been updated, and there's no consensus on anything at all. The same I did with codes, building codes. We went through 325 seismic and masonry codes in original languages. I saw some people here joining today that helped me with translating this in their original language. What we now see today is that only 7 countries allow it, and it's going to be 6 because Georgia is moving to Eurocode, and Eurocode says that it's basically ashlar only, which means cut blocks. So that means that stone masonry is completely not allowed in, for example, Pakistan, Afghanistan, Yemen, and Bhutan don't even have a seismic code to begin with. But also in Turkey, we see now around the cities a lot of damage in villages which were made of stone masonry. It doesn't help these countries at all if we just forbid it, because like I said, it can be done. But also here, no consensus on anything. So this is, for example, a house in India is allowed only up to 0.08 G, 2-story, quite small volume. In Tajikistan, it is allowed up to 0.40 G, massive volume. There's such a difference between these countries. And with schools, it even becomes worse because India and Nepal, even though many places, yeah, this is what we can, this is the material used for schools. It's basically not allowed, but the codes are not 100% clear about it. So this is why they are between brackets. But look at the difference between just one classroom in Iran versus what is allowed in Tajikistan. It's such a massive imbalance there. All right. So I think I've now proven that we've lost the basics also. So we need clear terminology, that's one thing. And we need to start finding those basics again, because what we have now is yeah, a mess, in my opinion. And this is what I mean. All right. Someone asked in the previous presentation about cost implications. Well, this is unique information. I've never, ever seen this before done by anyone. And we were, well, lucky enough that, first of all, I made my estimates myself. But we did it super local, and the Nepalese let's say district rates. That means they don't make a distinction between a bag of cement bought in the city or a bag of cement that has to go I don't know, 3,000 meters up, because the price is sort of the same for the whole district. So what we did is that we had super local data of transportation. We knew about roads, we knew about distances, we knew about how far people had to carry this and what the cost is of carrying this bag of cement, which of course becomes 3 or 4 times more expensive to get it up on the hill. So we had this, we had a whole map of the region of 20 different villages, and we did a very detailed cost comparison. So what we did is we also said, okay, sometimes you have the good quality of sand, so that's nice, close to your river. If you don't have it, if you have very fine sand, we're going to put a little bit more money into the estimate so that you can get the sand from a little bit further. Do you have a local wood, yes or no? And so on and so on. So we had super detailed data, and we could calculate completely from, okay, this is my school is fully reinforced. Then there was one of the experts that said, well, I have this great idea of removing bands. It's going to bring us a massive cost saving. So now, normally I also ask in the group, okay, what do you think? Removing 2 horizontal bands, what is the cost saving in terms of total cost saving of the budget? But let's not do it today. I can already tell you that the most given answer is that people think that removing 2 of these horizontal bands saves us about 15 to 30%. This is the reality. It is only 2. In the best case, removing 2 bands is just 2% of the total budget. So at first, I was quite disappointed about this. I thought, okay, come on. This is not going to give us the big cost savings that we were hoping for, 1 million of these buildings minus 2 bands. What I didn't realize at the moment, is that if I remove one of these horizontal bands, there will be a layer of stones with cement in return, and that is almost the same price. So actually, this is super good news. The super good news here is that a band doesn't cost so much in this system. So why not put it in? Because these bands are super important. So it is actually the best news ever. So these bands are not so expensive, and they should be in there. Simple as that. That doesn't mean that we should throw in 7 like the German organization tried to do. But the news is good. It is not so expensive. What is expensive is that this fully unreinforced building, so that has nothing, that's mud mortar, no reinforcements, a weak roof, and so on, versus me doing everything, is 83% more, let's say roughly 80% more. Now, of course, that is a big amount, especially for people there. That is a massive amount, and it's an investment that you must be willing to make. Of course, for us, it's a no-brainer. We think, hey, come on. And even for us in the West, this is like very low numbers. But okay, what I also found out is this, is that the mortar, so going from mud to cement mortar in the walls, is just 30% more. That's not so much, actually. I was surprised about that amount. It's just 13% of the total budget. The bands altogether, all the 5 bands, is about 15%. The tie beam is the most expensive of that one. It's about 5%. But what is interesting is that these most important reinforcements, mortar and bands, is almost the same amount as finishing. So putting these aprons with this plastering, putting this plaster and paint on the inside, putting this valance board, which is that wooden strip of finishing here, that together is the same as the most important reinforcements. So if your budget is low, and wait with the finishing, that can come later. Do a bit of saving later on and finish it later on, but start with those most important reinforcements. That's my message. So good news, the horizontal bands are not that expensive. That is actually very good news, and it is unique information. I have never ever seen this before. Cement mortar is expensive, we know that, but I also want to get rid a little bit of the story that it is difficult to get cement at all these remote places, because just go to any place on the mountains in Nepal and you will be able to buy Coca-Cola there. I mean, in that regard, it is, I understand that it is expensive, but it is not impossible anymore. It is absolutely, I disagree with that statement. It is, finishing can be postponed, but it is a matter of prioritization. If you can get Coca-Cola there, you can also get a bag of cement there. So very good news as far as I'm concerned. It is not that expensive to do the most important reinforcements. Imagine what will happen if we can prove that we can do it with mud mortar. but that's a different story. All right, this is then the last bit of my PhD, where we did a base shear seismic demand comparison. I'm going to do this quick because I don't want to go into too much detail, but we did it on a global scale with the most important codes and the codes, the countries that still allow stonemasonry. We followed this literally. We came up with a conceptual base shear formula, which I'm not going to explain here. We started comparing countries, seismic hazard in countries. For example, India. I gave this presentation 2 months ago in India as well. So this is why there's some Indian examples in here. But the Indian seismic hazard is immediately halved. So only 50% is considered as design earthquake. But then what we see is that we see massive gaps. This is the Himalayan belt. And then you see, for example, that Afghanistan and Pakistan, they calculate with very high values. And then all of a sudden India with only half that value. And then again, Nepal with high values, a little bit India, and then Bhutan again with high values. This, by the way, a seismic map. Bhutan doesn't have a seismic code. But just to show you that also between countries and bordering countries, there's such a big difference in how this is approached. And that should also be leveled more realistically. We looked at response spectra, we looked at distribution of forces, we looked at redistribution of forces over the panels, and so on and so on. I don't want to go into that. The conclusion was very simple, actually. The seismic codes are not written for masonry, but they are written for concrete and steel frame buildings. And what you see in a building like this is that most of the mass is in the floor, where opposed to my buildings, most of the mass is in the walls. Actually, 98% of this building is masonry. It is a masonry shell with holes in it, and the floor and the roof is only about 2% of the total mass. So it means that the seismic codes as they are basically not meant for this. And that is then our third conclusion. We need standalone codes. So far, I've only talked about this. We went through tons and tons and tons of data and so on, but we can bring it back to three very simple conclusions. We need a clear terminology. We need to be very clear about what type of masonry and the differences between different stone types. We need to find the basics again, and we need to come up with something that is standalone, because otherwise it will not meet the needs in the field where this still is used, this technique. But this is probably the most important word, is acknowledgement, because I have shown you now in, let's say, 20 minutes where we are today. I dare say that it is a bit messy. It is very confusing. It is contradicting. It is not complete. But the only way how we can get this to the next level is that we first must acknowledge that. We can do two things now. We can say, wait a minute, we have done this for 40 years. It's fine. Or we say very clearly, no, enough. Enough is enough. There's so many people still living in this, and we must give them something that is useful to them. So enough is enough. And I came to this conclusion. I said, I've had more than enough of this now. Let's do it. So I developed an international call to action, which is the following. Point one is that the high-tech seismic design, so let's say concrete and steel, that is based on peer-reviewed scientific research. And building codes are based on this. But for low-tech seismic design or non-engineered seismic design, it is not based on any peer-reviewed scientific research. It is based on, let's hope for the best. It is based on rule of thumb, and they are at this point not fit for purpose. I think I've shown that in this presentation. And so it starts with that acknowledgement. If we don't acknowledge that something is wrong, if we don't acknowledge that we are not up to standard, yeah, then it will never change. So this is, to me, probably the most important word, acknowledgement. And then only we can say, okay, now let's try to do this with today's state of the art, with some scientific research, that we say, let's go through all these motions and figure out what it is, and then bring it back to the level of the mason or to the people in the field. Let's come up, let's design, let's develop manuals that are simple and can be used by people in the field. This is my international call to action. And ironically, I'm not the first person who makes this, because already in 1977, Professor Arya said exactly the same. He said that at that point, the review of earthquake codes shows that much of the information is empirically based and not theoretically derived, and that it should be reviewed and improved over time. And it's unfortunately, it just didn't happen so far. So this is what we try to do. We is, well, me plus a number of experts that have joined. We call this SMARTnet. SMARTnet stands for Seismic Methodologies and Applied Research and Testing of Non-Engineered Techniques. And I'm going to ask you to join, because the case I've made today for stone masonry, I can also make for earth and structures. I can even make some cases for confined masonry. There is so much to be done. So what we are doing today now is, okay, we try to get this to the next level with a group of experts and some quite renowned experts and students. We are now doing a full assessment of 2 case study buildings. I myself are doing everything by hand. The experts are doing this with the computer modeling. And then we're going to see if we can extract a simplified method that is helpful to basically anywhere where people want to build with this. We are following the main codes, Europe, India, China, Russia, and also USA, because that basically covers everything. We start with my school and a typical Nepalese house, and we're just going to calculate whatever needs to be calculated with whatever models we can find, and just see if we can figure out what this is supposed to handle. So out of plane is not an issue, we know, because of the horizontal bands, but we're going to do it anyway. We just want to rule it out once and for all and never have to look back at this. But this is a bigger issue in plane. In plane is difficult to meet, especially when we still keep in mind that the codes refer to unreinforced. So there's no sort of calculation method at all at the moment that includes these bands. So for unreinforced, we can't even meet 0.04G, which is completely, of course, out of balance when we see my schools, of course, with bands that have withstood 35G. So this is what I mean. The codes tell us it can't be done, and this is why it's forbidden. But in reality, we say, yeah, but it can be done, but now we need to prove it so that we can get it back into the codes. So that's what we try to do. So we're doing now a benchmark, and we're going to try to do some, the modeling. The key here is material properties. So material properties of steel and concrete are very well known, but for stone masonry, they're very unknown, and especially for stone masonry with cement mortar. I mean, with lime mortar, quite a lot has been done, but nothing has been done for cement mortar or mud mortar. So what we try to do is that we make it local. So, for example, this is a picture I took in Indonesia. This guy is mixing mortar, but I also took the picture 30 seconds before this, where he lost half of his cement. Now this is very standard practice in all these countries. He was supposed to mix 1:4 or 5 or whatever, and it's now 1:10. This is a bag of cement in Nepal. It already started to harden due to moisture in the bag, but people they invested $5 for this. So they're going to crush this old cement, which is doing nothing, and kick it back into the mix. This is standard way of making concrete. This guy is plastering with a slipper. We have already seen him. But I mean, this is standard practice, and it needs to somehow go into our calculations because it needs to reflect realistic design. So we're at the moment testing low strength mortars. Some tests have been done in India recently on stone masonry specimens, so that we can put this in our models. This is very initial output. It needs to be verified with more partners, but the Indian model shows that anything over 4 bands is not doing anything extra to begin with. So this is sort of what we already thought. And this is an initial model from our Nepalese partner that shows that the vertical steel is not basically adding anything. But again, this is very initial data. Long story short, we are going through the high motions, but in the end, we need to bring it back to a very simplified method because this mason only needs to know how long and how wide it should be. So that's what we try to do with SMARTnet. And as I said, we need help. We invite everyone to join, either with the stone masonry, but feel free to start up your own line with Adobe, with rammed earth, with whatever technique. Just follow our methodology. I mean, that's also what we try to do. We try to sort of show a way how to do it. First of all, we show that it is very necessary, and then we have some ideas on how to do it, and feel free to follow. So acknowledgement, I've said it already, and I'm going to slowly finish up with my last thing that I want to say about this. Acknowledgement, this is where it starts. Are we going to say today, yes, enough is enough, we're going to try to figure it out? The technological side of things have shown, but there's another thing, which is the environment. We need to do this for a second reason, which is if we want to meet the Sustainable Development Goals, we need to also acknowledge that the building construction is one of the main polluters. We know this of the annual global CO2 emissions, building related activities, and especially production of concrete, steel, and aluminum is almost a quarter of the annual global emissions. So what we should do is promote natural materials, promote traditional techniques more as well. So like I said, I've given this not so long ago in India. I've shown them this picture where this is the air pollution due to all kinds of exhaust. The thing here is that the technological strategy, like I already explained, validation of solutions, that's one thing. But the promotion of nature-based solution is also going to help here. So I'm very much in favor of this techniques. This is the school I built in India myself with stabilized earth blocks. Very easy to make earthquake resistant, but it is mainly earth, and we used quarry dust as a waste product as replacement for sand and just a little bit of cement. And then the next step is design. So one of the main critiques on, let's say, traditional techniques is that it looks for this is something for the poor, and that is absolute nonsense as well. This is the same block. It is an earthen block, but it is a very nicely designed example in Colombia, which is a highly seismic zone. So I'm hoping that something has been done here in terms of seismic improvements. But I'm just saying that it is two things. It is technique, it is environment, and it is also design. It must look appealing, because then more people will start accepting this. So whether it is rammed earth or adobe, it is a matter of design. It is using traditional techniques that we know that behaved better. This is Batar in the north of Pakistan, for example. It has withstood the 2005 Kashmir earthquakes. Many of these techniques, and also Daji Dewari, have withstood the earthquake where all the concrete block houses collapsed around it. This is a Turkish example of Himish. I took this picture in Bursa, which is close to where the Izmit earthquake was in 1998. What you see in the back is a concrete block. The people there told me that everything behind this house collapsed, but then again in concrete they rebuilt this. This house survived many earthquakes, but it looks poor. So that's the issue. So rather than saying, hey, this can't be done, it is now a matter of reintroducing this in my mind and make it look pretty. That's it. Then all of a sudden, so we need proof, and it needs to look acceptable, and then we can start contributing to the Sustainable Development Goals. There's an example in Greece. And then I say, okay, if this is done in Greece, which is a highly seismic region, somehow this, I suppose this has been made earthquake resistant, or some level of research has gone through this, then that should then trickle back to my buildings in the Himalayan or Middle East or wherever. So there should also be cross exchange of knowledge between certain countries. So the research should take place at different countries at different levels. And again, it's a matter of design. Everybody likes this, everybody accepts this. So now we need to prove it that it can be done, and then it needs to look acceptable. I think that is clear. This is, I think, one of the last examples. Again, I show the picture of India. This is a picture after the harvest period. So what you see there is that there's so much smoke in the air of burning crops and burning straw. Globally, the crop burning is about 3.5% of all the CO2 emissions. Same story, works beautifully in an earthquake. It has some flexibility. It's just a matter of design. So I think I made my point well enough now. It's about acknowledgement on a technological level. It's about acknowledgement on an environmental level. And we just now need to do it. We need to push this better. So my call to action now needs to become action. That's the point I wanted to make today as well. I think this is the end of it. Yes. So long story, too much information maybe, but this is my email addresses that you can reach me. But my question is, please join. We need less concrete and steel. We need more traditional techniques and natural materials, but it must be safe and it must be healthy. The end. Is there any question?
Thank you very much, Martin. We have questions in the chat box. If you can follow, please.
Yes.
So maybe we start from the, give me 1 second. If you go up scrolling, okay.
See here, this is a question about,
Yeah, Andrew,
yeah,
255, if you start from there.
So the question about, well, which materials can be used for, well, natural building, I think I already probably answered it by some, but earth is of course one, wood or wood laced or wood frame is of course another one. Straw bales could be a very nice one, but also bamboo, although bamboo has some issues in terms of it should never be exposed basically to the sun and the moist, but that has some flexibility. But yeah, basically whatever I've shown today, and this is what I wanted to show you, the difference between, let's say, what I did 10 years ago, where I followed some rule of thumb, and then at some point I started questioning them, and at some point we recognized the need for deep technological research to get things more generally accepted. So rather than just throwing it out of the building codes, it needs to be reintroduced, but in a sensible and safe way. So whatever material or technique we then choose, so I go with stone masonry, but like I said, stabilized earth blocks, straw bales or whatever, it needs to go to all these levels of deeper research. I mean, we need to get rid of that the rule of thumb, the best practice, whatever that means, terminology. It just needs to be proven, because with proper proof, we make a much stronger case to get these things reintroduced into building codes. And I think it's very necessary, not only in terms of safety, but also in terms of health and environment, because the world is not in the best state at the moment. And I believe that these techniques can really contribute to this, but we have a long way to go.
Okay, the next question from Dinesh, in case of Nepalese schools you built, 301.
Wait, am I going too fast? .301, you say? Oh wait, you're in a different time zone than me. 401 then.
Okay, sorry.
Yeah.
Yeah. So Dinesh.
Oh yeah, okay. In case of the school building constructed in Nepal before 2006, do you know that? Yeah, I know how. Yeah, well, I've shown that. I think in one of the pictures, we had no damage at all, basically. Have you seen that picture, Dinesh? Otherwise, I can put it here again. But yeah, we had no damage. That's fair to say. We had some hairline cracks. This one. This is what we had at worst. Some hairline cracks in the plaster. That's it. So yeah, they behaved very well in the earthquake. No damage. Shall I move on to the next? This we had already from Peru. Yeah. I know this one. I'm in contact with Marcel Blondet for a long time, and I really admire this work. This is sort of the level that I hope to achieve in a few years from now with the stone masonry. That we say, yeah, can be done. Yeah, no, absolutely. I really admire the work of all the Adobe research in Peru with this whole team. So yeah, thank you. Yeah. SMARTnet.org. The idea here was to create a website where people sort of in the world could plug in and say, okay, I'm living here, and then that we could give some suggestions of what could be built there, and we could give some manuals that meets that certain typology or material or whatever. That was the idea. But the thing is that by now I learned the hard way that this research takes very long in some cases. And I'm not going to post anything as, let's say, a final manual before we have more justification of how these things work. So for us to start this interactive sort of SMARTnet website, we thought, okay, doesn't make any sense to do it now, because by the time that we have some really decent results on this, that is already, we are years behind with the technology. So with the website technology. So SMARTnet is at this point is the overall project name, and nothing more at the moment. So the website, that might take a while, but the project in itself is up and running. If you want to join, please join. Can you apply some of your wisdom on quakes? Can also be applied on our home of floods. Oof. There we have Mr. Brouwer again. Shall I do this in person to you, sir? No, let's not do that now. Floods is a different horrible type of disaster. No, I can't answer that very quickly now. Let's not do that here. I will get back to you, sir. Any information about the seismic design of Adobe? Yeah, okay. Back to the few posts back, there is beautiful research done in Peru. The thing, what I can say about it in 2 words is that it is fairly limited dimensions. But okay, that's the consequence of working with a brittle material, and then with some geomesh and some tying of meshes around it, it really can withstand quite heavy earthquakes. So if you can go back to a few posts and maybe contact each other directly, yes, it can be done. What time scale do you see for this work? Oh man, if only I wish. Yeah. We're talking about a few more years for sure. We're going through many levels of this. So like I said, I'm doing hand calculations just to see what is there. Then we're going to do modeling. Then at some point this will come sort of, there will be some leveling up here in terms of that we think, okay, this is what we think it should be done. And then probably we have to do a shake table to prove it. This is going to take a while.
I think we should cover the already asked questions, and then
yeah,
we should finish because we are running out of time now.
All right.
No.
What I suggest is any further questions, just give me an email and we can talk some further with whoever wants to know whatever.
Of course. Okay. I think that's it. A very good presentation. Well done, Martin. And thank you very much for accepting the invitation for the talk. And I hope all the participants enjoyed it, learned from it, and they will contact Martin for any further questions or any help they can provide Martin on his project. So about the upcoming course, let me share one slide. So this is the upcoming course from the UNESCO Chair at UCL, and this is happening 2 days presentation, 9 and 10th of March, same time, 2 to 4, and it's all online. The speakers are Pierre, Jiyun, and Asana from France, Glasgow, and UCL. So this will be an interesting talk on the system resilience. These are different components of the systems. So this is about network, application of Bayesian networks for decision-making in civil engineering problems. So this will include the individual components, for example, the road infrastructure, the schools, and the logistics and all. So this will be interesting, and I request you all to register for this. So we will publicize this event in our website very soon. And please follow our website and do register for the event. I thank you very much for all the participants, and thank you, of course, to Martin for an interesting and very useful talk. Thank you very much. Okay, that ends the presentation for now. So we will see you next time. Thank you very much. Bye-bye.